Hey everybody, this is Mr. Schultz here with you. We're going to take a look at 9.1.4, day 2. What kind of a number is it? So we're talking about rational and irrational numbers, which are all part of this real number system. And so rational numbers and irrational. All right, so let's take a look at what we did on day 1 first, and then we'll keep going. All right, so from this problem from yesterday, which is 9-53, it says Jessica knows that 0.57 repeating is a rational number, so she needs to be able to write it as a fraction. We just said that she wrote it as 57 over 100, which we said that was 0.57, and that is not equal to 0.575757, because that's what it is to repeat. It just keeps going on and on and on. So the real question then becomes, how do you write 0.57 repeating as a fraction? How do you write that as a fraction? Well, we know it should be pretty close to 57 or to 57 over 100, because that's pretty close, but it just doesn't get quite that repeating thing. So let's take a look at the next question and see what we can find out. So on 9-54 here, it says, to help Jessica with her problem, find the decimal equivalents for the fractions below. So here's what I'd like you to do. Pause the video and come up with what are these 6 decimal equivalents here. And we'll bring it back in. So take a second to look at these. All right, so here are your decimal equivalents. So on A, the 19 over 99 is 0.19 repeating. 391 over 999, well, that's 0.391 repeating. 3 over 9, well, that's just 0.3 repeating. 1 over 999 is 0.001 repeating. So we can start to see that so this next part here in part G says, what patterns do you see between the fractions and their equivalent decimals? Well, it seems to be that if you put it over 999 or 99 or 9, if you put it over 9, that's what's making the number end up repeat when you are going through here. So going back to Jessica's, if it was 57, we just want to do 57 over 99. So whatever number you're looking to have repeat, you just put the same number of place values in 9. So if I was looking to repeat the number 321, I would do 321. That's got 3 place values, and I'll put that over 3 9s, and that'll give me that repeating decimal of 0.321, 0.321, 321, 321, 321, and so on and so forth. So using that pattern, what do we think the fraction is going to be for 0.24? Well, that's going to be, or 0.24 repeating, that's going to be 24 over 99. So when you plug that into the calculator, let's see what that does. And when we pull that up and do it, so 24 over 99, we get that 0.2424242424. And this is just the reduced form fraction there. But 24 over 99. So we've checked that with the calculator. It does seem to work out. So now it says use your pattern to go the other way now. So now what's the decimal equivalent for 65 over 99? Well, that should be 0.65 repeating, or 0.65 repeating. We're going to check that out with the calculator by just plugging that in and seeing what that looks like here. Let me just get there. So when I put 65 over 99, there it is, 0.65 repeating. And you might notice that right over here, it ends with 6.6. You might think, wait a second, did that repeat? So Desmos is just rounding it off there because this would be 6.5, and so basically, and then 6 is following. So the 6 makes this 5 go up 1. So it's creating that kind of rounded answer there. Let's take a look at the next one. So in 956 now, just got some examples here to try. So why don't you do this? Show that the following repeating decimals are rationals, because if it's rational, it can be written as a ratio or a fraction. So rewrite these rational repeating decimals here as a fraction to prove that they are rational numbers. So take a second, pause the video, and rewrite these as fractions. All right, so here should be your solutions. You've got 42 over 99 for part A. You've got 312 over 999 for part B, 16 over 99 for part C, and 8 over 9 for part D. So there you have all of your fractions as the repeating decimals being turned into fractions. Okay, so here we go. We're going to take a look at 957, which says this. Indicate the approximate location of the following real numbers on a number line. What can make this task easier? Try to do it without a calculator. So we're going to avoid the calculator here, and we're going to try to line up these numbers. So this is kind of a 7th grade thing, and I think that something that would make this easier would be to make the actual number line. And so here we are going to just go and we're going to try to roughly place each of these numbers here. So whenever I'm doing something like this, I usually try to target the things that I feel like I know how to do right away. So my first one at 2/3, well, that's just going to be 2/3 of the way between 0 and 1. So my 2/3, I'm going to put that at roughly 2/3. So this will be labeled as 2/3. Negative 0.75, well, that's going to be a similar thing, but it's just going to go down to -1. So negative 0.75 would be something like right there. Whoops, negative 0.75. Now I get to this square root of 8. I'm not really sure how to do this one yet, so I'm going to skip it. Negative 9/5. Well, that's got one whole, and then it's got 4 more negatives there. So I'm going to go past 1, and I'll go 4/5 of the way to -2. So 4/5 of the way would be negative 9/5. So I've got this one done. I've got pi over 3. Let's come back to that one. And 2 and 1/4. So I'm just going to go over to positive 2 and go just a little bit beyond it here. And call it going over to 1, 2, and then 1/4 of the way to 3. Should be somewhere like here. So these are kind of my more straightforward answers. So my things that I have left now, I've got the square root of 8, and I've got pi divided by 3. Let's take a look at pi. Well, pi is just a number. And remember in 7th grade, we rounded it. We called it 3.14. So this is essentially 3.14 over 3. Well, 3 over 3, that's just 1. So this is really 1.14. It's somewhere right around there. So I'm just going to go over to 1. And I'm just going to go a little bit beyond. 0.14, that's 1400ths. So I'm talking about just being about a little bit more than about 1/10 of the way, or 10/100ths of the way. So maybe somewhere right about here would be pi over 3. Okay, now we get to our last one, the square root of 8. Well, that every time we've done square roots, we've just plugged into our calculator and found some sort of a decimal. How are we going to tackle this? Let's take a look at the things we know about square roots. Well, we know some square roots. We know like the square root of 1, well, that's just equal to 1. We also know that the square root of 4 is equal to 2, because that's just saying 2. This is just saying that 2 times 2 is 4. 1 times 1 is 1. The square root of 9 is equal to 3. The square root of 16 is equal to 4. So I'm basically just taking all of my counting numbers here. I'm multiplying them by themselves. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. So, but these are the nice and whole numbers. Well, if I think about the square root of 8, the square root of 8, in theory, should fall somewhere between 4 and 9, because 8 is between 4 and 9. And in fact, it should be pretty close to 9, because it's just one number difference between 8 and 9, whereas it's 4 numbers of difference between 8 and 4. So probably it's going to be pretty close to 3, but not quite 3. So I'm going to put the square root of 8 somewhere over here. I'm going to put it close to 3, but not quite 3. Now, I know it says to not use a calculator, but let's just see how close our guess is here. Is it close to 3? Okay, so here, when I do this, I'm going to take the square root key, and I'm going to put 8 in there. And look at that. I'm sitting right around 2.82. So pretty close to 3, 2.8. That's pretty close to 3. It's not quite 3, but it's pretty close. So looks like our estimate is fairly solid there. So basically, that's what you can do to estimate any sort of square root. So if I gave you the square root of 15, well, you'd say, hey, that's close to 16, so that means it should be close to 4. Let's call it maybe 3.8 or 3.9, something like that. We basically just make out your list of your squares or your perfect squares and go, okay, it has to be close to some of those numbers and go from there. So let's practice that a little bit more on the next problem. So my next problem is 9-58, and it just says, without a calculator, order the numbers from least to greatest. Well, I've got a couple of nice and even numbers here, but then I've got these square roots as well. Let's start off by ordering the things that we know and then go from there. So 10, well, that's just 10, so we'll just start there, and we'll see what's around it. 3 pi, well, that's 3 times by 3.14. So I can just do some multiplication of decimals here. 3 times 4 is 12. 3 times 3 is 1, plus that 1 from the 12 is 4. 3 times 3 is 9. Then I'll drop down the decimal, so 9.42. So 3 times by pi should be less than 10. So I'm going to put that to the left of 10. We'll come back again to these square roots because we'll practice those. 1.1 times by 10 to the first. Well, 10 to the first just means move this one time, so I'm actually talking about the number 11.0. Well, that's obviously going to be bigger than 10. So I've got that, I've got 10, I've got 3 pi. 9.099, well, that's going to be smaller than what we found with 9.42. So I'm going to put 9.099 to the left of 3 pi. And now I've just got my last two here. So let's practice this writing these or estimating these square roots here. So again, I'm going to write out my perfect squares, and I'm going to do that just by writing out the counting numbers first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll even go up to 11 just in case we need it. And then all I have to do is say, well, the square root of 1 is just 1 times by 1. So that's going to be 1. To get to the round number of 2, that should be 2 times by 2. So that's 4. Get to 3. 3 times by 3 is 9. 4 times by 4 is 16. And so on and so forth. Okay, so I wrote out the rest of the squares here. So now I just need to look at these two numbers and go, okay, where do they place? Well, starting with the square root of 99, well, that's definitely larger than 1, 4, 9, 16, 25, 36, and so on and so forth. We get to 100, and it's not larger than that. But it is larger than 81. So I know that the square root of 99 has to go between 9 and 10. And when I think about it, when I think about the distance, it is a long ways from 81, but it's really close to 100. It's actually just one number away. So this number should be not really close to 9, but really close to 10. It's probably at 9.9 or something right around there, because it should be a number very close to 10, but not quite 10. So if it's very close to 10, but not quite 10, I'm going to put that right next to the 10, because 10 will be bigger than it, but just barely. So that gets me the square root of 99. Now, same thing with 102, but this time we notice that it should be bigger than 100, but less than 121. So this one is going to be between 10 and 11. But again, it's going to be closer to 100. It's only 2 away from 100. So if I were to make this into kind of a longer chart here, I'm just going to blow up this kind of in between 10 and 100. The square root of 100 is 10. And the square root of 121 is there. So if I think about the distance here, the distance from 102 to 121, that's a distance of 19 numbers, where it's only a distance of 2 numbers going down to 10. So it should be pretty close to 10, just a little bit bigger than it. So I'm going to put the square root of 102 after the 10. So our final list here should look something like this: 9.099. It should be 3 pi, which we said was 9.42, the square root of 99, 10, the square root of 102, and 11. And that'll be our list here of our numbers, which I guess I should call 11 the scientific notation one, which is 1.1 times by 10 to the first power. Okay, that should be everything that we have for today. If you have any questions, feel free to reach out to your teacher. Thank you so much. Bye-bye.